In this presentation, I'm going to explain the basics of stability. Stability is a vessel's ability to remain upright under a variety of conditions. And it's basically determined by the interaction of two forces. You have the force of gravity and the force of buoyancy. Force of gravity is the force that pulls all things down to the earth. So the force of gravity is pulling down on the vessel. The force of buoyancy is the force created from the vessel displacing the water. So when you put the vessel in the water, it pushes some of that water out of the way, and the water pushes back by trying to refill that space. So it exerts a force on the bottom of the vessel, an upward force. So those two forces, the force of gravity and the force of buoyancy, are working against one another. So one's pushing up, one's pulling down. Okay, when talking about the vessel and talking about how these two forces interact on a vessel, we need to keep in mind two reference points. So first reference point we'll talk about is the center of gravity. So we'll say that this is the vessel's center of gravity. We're going to label it G. So G is the center of gravity. You can think of the center of gravity as sort of the balance point of the vessel. It's the point where the vessel's weight and all of its contents, it's the point through which the vessel's weight and all of its contents interact. Okay, so it's better to think, it might be easier to think of it as the balance point. So for example, if I wanted to find the center of gravity of this marker, I would find out where this marker balances. Okay, so that's the center of gravity. So now another reference point that we have to keep in mind is what we call the center of buoyancy. So we'll label on this vessel B. So B is the center of buoyancy. So the center of buoyancy is the point where the upward force of buoyancy, it's the point through which the upward force of buoyancy acts. It's kind of the balance point of that force. So now, one thing I'll explain about the center of gravity is that if you don't move any of the weight in or on the vessel, that point will stay static. The center of gravity will not move. So the center of gravity of this marker isn't going to move unless I change the weight in the marker. Okay, so the balance point won't shift. Okay. However, the center of buoyancy is a function of the shape of the water being displaced. Now remember how I said the force of buoyancy is created by the displacement of the water. And so depending on how that water is displaced and the shape of that water, it can determine where this balance point is. Okay, so center of buoyancy, center of gravity. So now we're going to assume that this vessel is symmetrical. The port side is the same shape as the starboard side. That being said, the center of buoyancy will be right along here, right along the center line. And we'll say that being that the vessel has the same weight, port and starboard, that it will be directly underneath our center of gravity. So in a sense, this vessel is going to be sitting at equilibrium. So these two forces have balanced each other out, and the vessel is sitting in a static position. Okay, now, a couple things I want to explain. That being said, being that the force of, or the center of buoyancy is a function of the shape of the water that's being displaced. If we were to start to tip this vessel by an external force, if we're not shifting any of the weight on board, say for example a gust of wind came and started tipping the vessel, it's what we call heeling. Heeling is the tipping of a vessel caused by an external force. If it were caused by a shift in the center of gravity, we call that a list, if it's leaning due to a shift in the center of gravity. But we're going to say that the vessel is heeling. We'll say that the wind is starting to tip that vessel. Now remember, the force, or the center of gravity, has not changed its location. That's static because we haven't changed any of the weight in the vessel. Now, because we tipped that vessel, we've actually changed the shape of the water being displaced. So that being said, the center of buoyancy is going to change its location. Under this circumstance, we've tipped the vessel to the starboard side through force of heeling, so we'll say it was wind. And you'll notice here that on this side, the port side, there's less water being displaced on this side. So that being said, the force of buoyancy is going to be more on this side than on the port side. So that means the center of buoyancy has shifted, okay? So in this case, we'll say that the center of buoyancy is shifted here. Now notice they're not directly on top of, or they're not directly in line with one another. One thing I have to point out too is that the force of gravity pulls perpendicular to the surface of the earth. The force of buoyancy pushes up perpendicular to the surface of the water. Okay. Now a couple other things I want to point out. I want to explain to you another reference point that we use in naval architecture. But first, I'll fill in my reference lines. Okay, so this green dotted line is showing the center line of the vessel upon which the center of gravity is located. So this other line that I'm going to draw is a line going up from the center of buoyancy perpendicular to the surface of the water. Okay, just like that. Okay, this line is it's basically showing the direction of force of buoyancy on the vessel. So buoyancy is pushing up in this direction, perpendicular to the surface of the water. So now you have gravity pulling down perpendicular to the surface of the earth. Okay, so we have this center line here, we have the force of buoyancy. Now those two lines, when the vessel is heeling like that, intersect right here at this point that we call the metacenter. We're going to label that M. It's called the metacenter. Okay, the metacenter is a theoretical reference point that they use in naval architecture to try to determine the vessel stability. There's no particular piece of the vessel that corresponds to the metacenter. It's sort of an abstract reference point. And hence the name meta, with the prefix meta, kind of signifies that it's abstract. So it's just a reference point where these two lines intersect. Okay. Now, there's a distance that we also want to remember. That's GM. We call that distance the metacentric height. Okay, now the metacentric height is this distance right here. Okay, it's a theoretical distance, but by determining the metacentric height of a vessel, we can kind of determine what the vessel's ability to turn upright, or the vessel's stability. And I'll explain that here by explaining another distance. First, I want to point out, though, notice that these two are right on top of one another. So they're interacting with one another in a balanced way. It's keeping the vessels sitting upright. It's in equilibrium. However, when that wind started blowing the vessel over, causing it to heel, the center of buoyancy shifted. Center of gravity stayed here. Now notice they're not directly on top of one another anymore. Okay. So that being said, there's a rotational force that's trying to turn the vessel back upright. So what I'm going to draw out here is another line. And I'm going to draw it perpendicular to the direction of gravity, but also perpendicular to the direction of buoyancy. and it's drawn it over from gravity over to this line corresponding to the force of the buoyancy. And where they intersect, I'm going to call that Z. Okay? Now that distance right there is what we refer to as the righting arm. Okay? Now remember I said these two points of force, center of gravity and center of buoyancy, are offset. That being said, there's a rotational force being created. Now the righting arm is sort of the measurement of that rotational force. So GZ, we'll call that the righting arm. It's another measurement you'll want to remember. You can think of the righting arm as sort of a wrench. If we imagine that there's a bolt right at the center of gravity fastened to the vessel, and this is a big wrench, and buoyancy is basically the hand that's grabbing the end of that wrench, and it's cranking that wrench around, turning the vessel upright. That's basically what the righting arm is. Okay, so that being said, the righting arm is what wants to turn the vessel, or the righting arm is the two forces interacting such that they're turning the vessel back upright. So again, think of it as a big wrench. Now, the righting arm changes length when the vessel tips. So, for example, the righting arm here is 0. Okay, it's sitting at equilibrium, so there isn't really a righting arm pushing one way or the other. So it's sitting static. Now when we start to tip that vessel, the righting arm starts growing as buoyancy starts to shift. As buoyancy starts to shift, this arm starts to grow. And it'll grow to a point where it reaches a maximum, and then it'll start to shrink. Okay, so that means, what this means is that when you start to tip that vessel, the rotational force to tip it back starts to increase, but then it reaches a point where it's maximum, and then you keep tipping the vessel and it starts decreasing. That righting force starts decreasing. So, if you tip the vessel too far, what happens is, I'm going to label here our center of gravity, and here's our center of buoyancy. Now remember, the center of gravity, again, hasn't changed. The center of buoyancy has, because it's a function of the shape of the water being displaced. Okay, now if I draw these reference lines in, we already have our green center line here, but I'm going to draw this line marking the force of buoyancy perpendicular to the surface of the water, and it's pushing up like this. And again, we have gravity pulling straight down to the earth. Now notice how these two points, or these points of force, are interacting. They're no longer working to right the vessel. They're working to tip the vessel over. So you have, they're offset. So we're going to draw our metacentric height, which suddenly is down here. Our metacentric height just went negative because it dropped below the center of gravity. Now, that being said, our righting arm has also gone negative. So instead of GZ, it's ZG. Okay? Now, when you get a negative righting arm like that, what we mean by that is you have gravity pulling down here, buoyancy pushing up over there, so it's creating a righting force, or it's creating a force turning the vessel, or a rotational force turning the vessel in the opposite direction. So here we have buoyancy pushing up, gravity pulling down, and it's giving you a net rotational force going that way. So counterclockwise, turning the vessel upright. Now here we got buoyancy pushing up, gravity pulling down, and it's suddenly going the opposite direction, in a clockwise direction. So that's trying to tip the vessel over. That's a negative righting arm. So if we were to want to graph this, this would give us what we would call a stability curve. Stability curves can be used to determine at what point, what angles of heel a vessel has a righting force to turn it back upright. It gives you an idea of the stability of the vessel. It can also give you an idea of what kind of conditions or what types of waters you would want to take that vessel out on. Give you an idea of how you want to handle that vessel. Okay, so I'm going to explain stability curve. I'm going to explain a stability curve by drawing a vertical axis. And I'm going to draw a horizontal axis. Okay, so what we're going to do is we're going to create a graphic representation of a vessel's ability to turn back upright. Okay, so where the two axes intersect, we're going to label that as 0. Okay, so the vertical axis is going to be our righting arm length. We'll call that GZ, because that's our righting arm. Okay, this is our righting arm length. So we'll just say it's 1 foot, 2 foot. It could be anything, any other unit of measurement, but we'll just say it's feet. Okay, so now this is the positive section of the graph. This is the negative section of the graph. Here's 0. So 0, 1, 2, 3, 0, negative 1, negative 2, negative 3. Now the horizontal axis here, that is what we're going to call our angle of heel. So basically the angle of heel is the angle at which the boat starts to tip. Okay, so this is 0 degrees because we're just sitting straight up and down. And then we tip. This could be, in theory, 20 degrees. So it's tipped over 20 degrees. And then here, this could be 120 degrees. We'll just say, just in theory. Okay, so that would be 120 degrees. Okay, if we were to want to graph the length of the righting arm at various degrees of heel, this would give us our stability curve. Okay, so here we are at 0 at the very beginning. There's no righting arm. The vessel's sitting at equilibrium. Now, as we start to tip, that righting arm grows. So we were to put here the different degrees of, or angles of heel. We could say 20 degrees. We'll say 20, 40, 60 degrees, and 80 degrees. Okay. If we were to plot that, so 20 degrees, we could say we got a 1 foot righting arm. And as you keep tipping the boat, that righting arm starts to plot to be bigger and bigger. But then you're going to reach a point where the righting arm reaches its maximum. And then as you start to tip the boat further, increasing the angle of heel, the righting arm here starts to decrease. Keeps going until it gets back to 0. Okay, so what that means is we've tipped that boat, buoyancy is shifted out, offset from gravity, this distance has increased, and then as we tip farther, they start to come together again. And where they end up over top of one another is back to 0. Now, at that point, there isn't a righting arm that's trying to push the boat either way. So it could be a balance point, but it's usually a pretty precarious balance point. It could fall one way or the other. Now, when you go beyond that, I have to move my letters out of the way. Okay, so this is our right angle of heel. Hopefully I'm not out of the screen. Okay, so when we go beyond that point, then we get a negative righting arm. If we were to plot the length of the righting arm for degrees of heel. So if we were to draw a curve connecting all of these plots, this gives us our stability curve. Okay, so here you see the righting arms growing, growing, growing. That means the vessel is there's a rotational force that's trying to turn the vessel back upright, and then it starts shrinking. There's still a force there. It still wants to go back upright, but then it reaches that 0 point, and then it goes negative. And when you're in the negative, that's where you're at this point. That means that the force of buoyancy and the force of gravity are working to tip you over. Now, in some vessels, they might go negative. The righting arm might turn negative at, say, 75 or 80 degrees of heel, which means if your vessel starts to tip to that point and go a little bit beyond, then chances are she's going to roll all the way over. Okay. Some vessels, especially a lot of sailing vessels, can go beyond 90 degrees before they get a negative righting moment. Some vessels can go all the way down to 110 degrees, and they can tip all the way over, and as long as you don't have any water entering the vessel, then that vessel will come back up. So you can tip her all the way over to 110 degrees, and then if the wind stops or whatever it is that's tipping her, she'll pop back up. Now, if they tip over and you have a hatch open or a port open, then water can flood in, and what that does is it changes the location of the center of gravity. And it can do it in such a way that would give it a negative righting moment, and then the vessel would tip over. So that's basically how stability works. That's how buoyancy and gravity interact to determine stability. And this is how we can determine a vessel's stability characteristics, or how we can look at a vessel's stability characteristics. So this can be important in getting to know a vessel and what her capabilities are going to be from a stability standpoint when you take her out in the water.